Today we're going to do 109 linear algebra true or false questions that will help you ace your final. In the description, there's a PDF containing all of the questions. I recommend trying the questions before you watch this video and pausing the video along the way so you have time to work out the questions on your own. So before you get started, smash the like button and join me in the simultaneous sip. Chapter 1. Linear Equations in Linear Algebra. Question 1. Every matrix is row equivalent to a unique matrix in echelon form. Well, that's false. Every matrix is row equivalent to a unique reduced echelon form matrix. Question 2. Any system of n equations in n variables has at most n solutions. Well, again, that's false. We can look at this system of equations, two equations in two variables, and if you solve it, you would see we have infinitely many solutions. That's way more than two. Number 3. If a system of linear equations has two different solutions, it must have infinitely many solutions. Of course, that's true. A system of equations has either 0, 1, or infinitely many solutions. So if it has two different solutions, it must have infinitely many solutions. Number 4. If a system of linear equations has no free variables, then it has a unique solution. Well, of course, that's false. Here we have a system of equations, three equations and two variables, and you could check this has no solutions, right? The first equation says x plus y equals 2. The last equation says x plus y equals 3. There's no solution to that. Number 5. If an augmented matrix AB is transformed into CD by elementary row operations, then the equation AX equals B and CX equals D have exactly the same solution sets. And you guessed it, it's true. AB and CD will be transformed into the same reduced echelon form matrix. And the reduced echelon form matrix determines the solution sets. Number 6. If a system AX equals B has more than one solution, then so does the system AX equals 0. Well, that's true. If AX equals B has more than one solution, then one of the columns of A must be a non-pivot column. And if A has a non-pivot column, then AX equals 0 will have more than one solution. Number 7. If A is an m by n matrix and the equation AX equals B is consistent for some B, then the columns of A span Rm. Well, that is just false. And for example, if A is the matrix 1, 0, 0, 0, 1, 0, and B is the vector 1, 0, 0, well then AX equals B is clearly consistent. B is one of the columns of A. But the columns of A definitely do not span all of R3. Number 8. If the augmented matrix AB can be transformed by elementary row operations into reduced echelon form, then the equation AX equals B is consistent. Well, that's false, because every augmented matrix can be transformed into reduced row echelon form, even inconsistent ones. And so, for example, if A is the matrix 1, 0, 0, 0, 1, 0, and B is the vector 0, 0, 1, well, you could check when you make an augmented matrix, it's in reduced row echelon form, and this definitely is an inconsistent equation. Number 9. If matrices A and B are row equivalent, they have the same reduced echelon form. And that, of course, is true. Each matrix is row equivalent to exactly one reduced row echelon form matrix. So let's say A was equivalent to U and B was row equivalent to V. Well, since A and B are row equivalent to each other, that would tell us that A is row equivalent to V and B is row equivalent to U. So U and V would be the same. It could be a good exercise to write this out as a proof. Number 10, the equation AX equals 0 has the trivial solution if and only if there are no free variables. That, of course, is false. The reason is the equation AX equals 0 always has the trivial solution, even if there are free variables. So take a look at the example I wrote out. If the matrix A is 1, 0, 0, 0, 1, 0, 1, 1, 0, well, the third variable would be a free variable, but AX equals 0 still has the trivial solution. Number 11. If A is an m by n matrix, and the equation AX equals B is consistent for every B in Rm, then A has m pivot columns. This is true. For AX equals B to be consistent for every B, then A has a pivot in every row. And since A is an m by n matrix, it has m rows. So it must have m pivot columns. Number 12. If an m by n matrix A has a pivot position in every row, then the equation AX equals B has a unique solution for each B in Rm. Well, that's false. This would be true if A had a pivot position in every column. And so a counterexample to this statement is if A is the matrix 1, 0, 0, 1, 1, 1. It has a pivot position in every row, yet if you tried to solve AX equals 0, then you could clearly see that would not have a unique solution. Number 13. If an n by n matrix A has n pivot positions, then the reduced echelon form of A is the n by n identity matrix. And that's true. A must have a pivot position in every row and column, which means the pivots are on the main diagonal. And if you have pivots on the main diagonal, your reduced row echelon form is the identity matrix. Number 14. If a 3 by 3 matrices A and B each have 3 pivot positions, then A can be transformed into B by elementary row operations. And this is, of course, true. Both A and B are row equivalent to the identity matrix. That's what we saw in the last question. So they must be row equivalent to each other. Number 15. If A is an m by n matrix, and if the equation AX equals B has at least 2 different solutions, and if the equation AX equals C is consistent, then the equation AX equals C has many solutions. Well, this is true. Since AX equals B has at least 2 solutions, we can conclude that A has a non-pivot column. So either we have 0 solutions or infinitely many solutions. And since AX equals C is consistent, it has at least 1 solution, so it must have infinitely many solutions. Number 16. If A and B are row equivalent m by n matrices, and if the columns of A span Rm, then so do the columns of B. And this is true. Since the columns of A span Rm, we know that A has a pivot in every row. And the pivot positions are determined by row equivalence. So B also has a pivot in every row. So the columns of B also span Rm. Number 17. If none of the vectors in the set v1, v2, v3 in R3 is a multiple of one of the other vectors, then S is linearly independent. And that's false. Here we could take S to be the set of 1, 0, 0, 0, 1, 0, and 1, 1, 0. None of these vectors is a multiple of the other one, but v3 is equal to the sum of v1 and v2. So they are linearly dependent. Number 18. If the set U, V, W is linearly independent, then U, V, and W are not in R2. And that's true, because the dimension of R2 is 2. So any set containing more than 2 vectors is automatically linearly dependent. And since there's 3 vectors and we say that they're linearly independent, we know they can't live in R2. No collection of 3 vectors is linearly independent in R2. Number 19. In some cases, it is possible for 4 vectors to span R5. Well, I don't know what world you live in, but here on Earth, that's not possible. Since the dimension of R5 is 5, any spanning set of R5 has to have at least 5 elements. Number 20. If U and V are in Rm, then negative U is in the span of U and V. And that is correct. The span of U and V is the set of all linear combinations of U and V. And we could express negative U as negative U plus 0V. And so it's clearly a linear combination of U and V. Number 21. If U, V, and W are non-zero vectors in R2, then U is a linear combination of V and W. Well, you may think that's true, but you're wrong. Here's a counterexample. U could be the vector 1, 0, V could be the vector 0, 1, and W could be the vector 0, 2. And clearly, U is not a linear combination of V and W, right? Any linear combination of V and W will have a 0 as its top entry, and U does not. Number 22. If W is a linear combination of U and V in Rn, then U is a combination of V and W. Again, this is false, and we're going to look at the same vectors that we looked at from the previous example. W is a linear combination of U and V here, right? It's 0U plus 2V. Yet we can't write U as a linear combination of V and W. Number 23. Suppose that vectors v1, v2, and v3 are in R5. v2 is not a multiple of v1, and v3 is not a linear combination of v1 and v2. Then the set v1, v2, v3 is linearly independent. And this is true, but maybe it's not immediately obvious. So let's just walk through a quick sketch of the proof. So to show that a set is linearly independent, we want to write out a linear combination of these vectors, set it equal to 0, and show that all of the weights must be 0. Okay, and so there's 2 cases we have to consider here. And I recommend you going through this proof on your own, trying to recreate it. So one case is if the coefficient of v3, which is c3, is equal to 0. Well, then that we could imply that c1 and c2 must also equal 0, because if not, then we could write v1 as a multiple of v2, right? And we said that v2 is not a multiple of v1. So Again, I didn't write out all the steps here, so you'd have to maybe write a little bit more details than this on a homework assignment, but this is the general idea. And if C3 is not equal to 0, well, then we could subtract over the C3 V3 and then divide by negative C3 to express V3 as a linear combination of V1 and V2. But we said that V3 is not a linear combination of V1 and V2. Thus, it's not the case that C3 does not equal 0, and we have that all of the weights are equal to 0, and our set is linearly independent. Good question. Number 24. If A is a 6 by 5 matrix, the linear transformation that maps X to AX cannot map R5 onto R6. And that is true. If we were to have a map that mapped R5 onto R6, or any map to map onto R6, our matrix would have to have 6 pivot rows, or rows that contain a pivot position. But our matrix only has 5 columns, and you could have at most 1 pivot per column, so we can't have 6 pivots. Number 25. If A is an m by n matrix with m pivot columns, then the linear transformation that maps X to AX is a 1-to-1 mapping. And this is false. This would be true if A had a pivot position in every column. And now notice here, A, which is the matrix 1, 0, 0, 1, 1, 1. A is a 2 by 3 matrix with 2 pivot columns, but the map that takes X to AX is not 1-to-1 because we would have a free variable. Now we're on to Chapter 2, Matrix Algebra. Number 26. If A and B are both m by n, then both AB transpose and A transpose B are defined. And that's true, and this is not that hard to check. A is an m by n matrix, and B transpose is an n by m matrix. So the number of columns of A is equal to the number of rows of B. So of course, AB transpose is defined, and it's an m by m matrix. Similarly, the number of columns of A transpose is equal to the number of rows of B. So A transpose B is defined, and in this case, it's an n by n matrix. Number 27. If AB equals C and C has 2 columns, then A has 2 columns. This one is false. If AB equals C, that means that the number of columns of A equals the number of rows of B, and the number of rows of A equals the number of rows of C. The number of columns of B is equal to the number of columns of C. So if C has 2 columns, it was the case that B had 2 columns. Number 28. Left multiplying a matrix B by a diagonal matrix A, so the only non-zero entries appear on the diagonal, with non-zero entries on the diagonal, scales the rows of B. And this is true, and this follows immediately from left multiplication. So there's a theorem that says the ith row of AB is equal to the ith row of A times the matrix B. And A is a diagonal matrix, so the ith row of A will have zeros in every entry. It'll have some number in the ith entry and zeros from everywhere else. And so if we take that vector and multiply it to the matrix B, it's easy to see that's just scaling the ith row of B by A. Do this out for yourself, see if it works out. Number 29. If BC equals BD, then C equals D. The number of you that say this on your homeworks or tests is incredible, but the answer is obviously false, right? Here's an example. If B equals the matrix 1, 0, 0, 0, and C is the matrix 1, 0, 0, 1, 1, 1, and D is some other matrix 1, 3, 0, 2, 1, 1, do out the multiplication. Okay? B times C is equal to B times D, and clearly C and D are not the same matrix. That's one of the most important properties of matrix multiplication. Here's another one, number 30. If A times C, so the matrix A times the matrix C equals 0, then either A equals 0, the 0 matrix, or C equals the 0 matrix. Again, that of course is false, right? And it's not too hard to come up with an example to show that this is false. Here we could have A be the matrix 1, 2, 0, 0, and C could be the matrix 0, 1, 0, 1, 0, 1. We do out this matrix multiplication, and you could check every entry is 0. But A is not the 0 matrix, and C is not the 0 matrix. Funny how that works. Number 31. If A and B are n by n matrices, then A plus B times A minus B is equal to A squared minus B squared. This, again, is false. And the reason why it's false is that matrix multiplication doesn't necessarily commute. So if we were to write out A plus B times A minus B, you could distribute it out and it would be A squared minus AB plus BA minus B squared. But the minus AB and plus BA don't cancel. Okay, so try to come up with an example to show that this one is false. Number 32. If AB equals I, then A is invertible. You may think this is true, but you're wrong. It's false. And there's a slight subtlety to it. A matrix that isn't square cannot be invertible. So if A is not a square matrix, then we automatically know it's not invertible. And so A could be the matrix 1, 0, 0, 1, 0, 0, and B could be the transpose of A. They multiply together and give us the identity, but since A is not a square matrix, it is not invertible. Number 33. If A and B are square and invertible, then AB is invertible, and AB inverse equals A inverse B inverse. Well, the first part is true. AB would be invertible, but the second part is not so true. AB inverse is equal to B inverse A inverse. So for example, if A is the matrix 1, 0, 1, 1, and B is the matrix 1, 1, 0, 1, then you could check that their product is 2, 1, 1, 1, and the inverse of their product is 1, negative 1, negative 1, 2. Yet the product A inverse times B inverse will give us 2, negative 1, negative 1, 1. These are not the same. Number 34. If AB equals BA, and if A is invertible, then A inverse B equals B A inverse. And this one happens to be true. And it's not immediately obvious why it's true, so we could work out a sketch of the proof. We'll start with A inverse B. Well, we can multiply on the right by A times A inverse, and that's not going to change anything, right? Because A times A inverse is the identity matrix. But then we have in the middle, we have a B times A. We could switch that to an A times B because AB equals BA. And now on the left, we have A inverse times A, which becomes the identity matrix. What we're left with is B A inverse. So A inverse B equals B A inverse. Number 35. If A is invertible and if R is not equal to 0, then the inverse of R times A is equal to R times the inverse of A. That, of course, is false, and it's not too hard to come up with a counterexample. We could take R to be 2, so it's not equal to 0, and A could be the identity matrix. Well, then the inverse of the identity matrix is still the identity matrix. R times A inverse would be 2 times the identity matrix, but the inverse of RA is not the same thing. Number 36. If A is a 3 by 3 matrix and the equation AX equals 1, 0, 0 has a unique solution, then A is invertible. And this is true. Since it has a unique solution, that means there are no free variables. Every column is a pivot column. And a square matrix that has every column as a pivot column is invertible. That's one of the 6 billion parts of the invertible matrix theorem. Now we're on to chapter 3, determinants. Number 37. If A is a 2 by 2 matrix with a 0 determinant, then one column of A is a multiple of the other. And this, of course, is true. The columns of A are linearly dependent because the determinant is 0. The only way for two vectors to be linearly dependent, so only way for two vectors to be linearly dependent, is if they are scalar multiples of each other. This, of course, is not true if there were more vectors, but since there's exactly two vectors, the only way for them to be linearly dependent is if they're scalar multiples of each other. Number 38. If two rows of a 3 by 3 matrix A are the same, then the determinant of A is equal to 0. This one is true. And the reason is, if the rows of A are linearly dependent, then the determinant of A is 0. So if two of the rows of A are the same, there's clearly a linear dependence between the rows. Number 39. If A is a 3 by 3 matrix, then the determinant of 5A is equal to 5 times the determinant of A. Now, a good way to check this before I say the answer is just write out an example. Okay, if you were asked this on a test or a quiz, don't just guess. Write out an example and see, does this ever hold? And so let's start with A being the identity matrix. Well, the determinant of 5 times the identity matrix would be 5 times 5 times 5, 125. And that is not equal to 5, which is the determinant of 5 times the of 5 times the determinant of the identity matrix. Okay? So this is best shown by just writing out one example, taking A to be the identity matrix. Number 40. If A and B are n by n matrices with the determinant of A equal to 2 and the determinant of B equal to 3, then the determinant of A plus B is equal to 5. Again, maybe it's not immediately obvious from the definition of a determinant whether this is true or not. So the first thing you should do is try to write out an example to see, does it work in this one example that you tried? And if it works, then maybe try to prove it's true. But if it doesn't work, you're done. You know it's false. So of course this one is false. We could take A to be the matrix 2, 0, 0, 1, right? Its determinant is 2. And B could be the matrix 3, 0, 0, 1. Its determinant is 3. Let's add those matrices together. We get 5, 0, 0, 2. And to find the determinant of A plus B, you just multiply 5 times 2, you get 10. You don't get 5. Okay, so this is clearly false. But again, this is a good example of one. Just write out an example. If you write out an example, a lot of these questions are clearly, a lot of the ones that are false are clearly false when you do an example. Number 41. If A is n by n and determinant of A is equal to 2, then the determinant of A to the third is equal to 6. What do you think we should do? How about let's write out an example and see if it holds. This one is clearly false. Right, A, again, we could take to be 2, 0, 0, 1. We multiply it to itself 3 times, we'd get the matrix 8, 0, 0, 1. The determinant of A to the third is 8. It's not 6. Number 42. If B is produced by interchanging 2 rows of A, then the determinant of B is equal to the determinant of A. Again, this one's false, And the best way to show it is just take any matrix and show it's false for that matrix. Okay, so we'll take A to be the identity matrix. You switch two rows. So B will be the matrix 0, 1, 1, 0. Well, the determinant of A is 1. The determinant of B is -1. Those aren't the same. Number 43. If B is produced by multiplying row 3 of A by 5, then the determinant of B is 5 times the determinant of A. And this is true. And this follows immediately from computing the cofactor expansion of the determinant of B along that third row. So if you were to write out the determinant of B in terms of the cofactor expansion along that third row, each term will have a 5 in it. You could factor it out and you'd be left with the determinant of A. 5 times the determinant of A. Number 44. The determinant of A is equal to negative the determinant of A transpose. Let's take a guess. False. How do we do it? We write out an example. Again, it's probably best to start with the identity matrix as an example. We take A to be identity, 1, 0, 0, 1. Oh, look, it's its own transpose. Okay, so how would taking the transpose make the determinant negative if it doesn't change the matrix at all? Right? They're the same. Determinant of A is always equal to the determinant of A transpose. I'm like getting irritated about these questions. Hopefully you guys are getting these right. Number 45. The determinant of negative A is equal to negative determinant of A. Wrong. The determinant, we could take A to be the identity matrix again. So negative A would be -1, 0, 0, -1. The determinant of negative A is 1, right? Multiply the entries down the main diagonal. But negative determinant of A is -1. 1 is not equal to -1. So a good question is, in general, what is the determinant of negative A in terms of the determinant of A? Think about that. 46. Assume that A is a square matrix. Then the determinant of A transpose A is greater than or equal to 0. Well, since we have that A is a square matrix, we could take the determinant of A transpose A and factor it as the determinant of A transpose times the determinant of A. But the determinant of A transpose is equal to the determinant of A. So the determinant of A transpose A is the same thing as the determinant of A squared. Any number squared is greater than or equal to 0. So this one is true. Number 47. If A to the third equals 0, then the determinant of A is equal to 0. Well, this is true. And the reason is the determinant of A to the third is equal to the determinant of A raised to the third power. So the determinant of the matrix A to the third is obviously 0 since it's a 0 matrix. And then the determinant of A, that number raised to the third power, must be 0. The only way that's possible is if the determinant of A equals 0. Again, I kind of was a little wordy with my answer, but this one works out pretty straightforward. Number 48. If A is invertible, then the determinant of A inverse is equal to the determinant of A. Well, let's take a look. It's false. In general, the determinant of A inverse is equal to 1 over the determinant of A. And just to see that from an example, if A is the matrix 2, 0, 0, 1, then A inverse is 1/2, 0, 0, 1. The determinant of A is 2, and the determinant of A inverse is 1/2. So they're not the same. Number 49. If A is invertible, then the determinant of A times the determinant of A inverse is equal to 1. This is true because, well, since A is invertible, we know that the determinant of A is not equal to 0. And we know the determinant of A inverse is equal to 1 over determinant of A. So this is not true if A is not invertible. 1, because A inverse wouldn't exist. Time for Chapter 4, Vector Spaces. Number 50. If V1 through Vp are in a vector space V, and the set V1 through Vp minus 1 spans V, then the set V1 through Vp spans V. Well, this is true. Since the set V1 through Vp minus 1 spans V, this means that the vector Vp can be expressed as a linear combination of the vectors V1 through Vp minus 1. Thus, the span of V1 through Vp minus 1 is equal to the span of V1 through Vp, which is equal to V. If the set V1 through Vp minus 1 is linearly independent, then so is the set V1 through Vp. This is obviously false, because Vp could be expressed as, it may be the case that Vp could be expressed as a linear combination of V1 through Vp minus 1. So for example, if P was equal to 3, for instance, V1 could be 1, 0, V2 could be 0, 1, and then V3 could be expressed as a linear combination of the previous two, even though V1 and V2 is a linearly independent set. Number 52. If V1 through Vp is linearly independent, then V1 through Vp is a basis for V. This is false, right? There's two conditions to be a basis. You need to be a linearly independent set, but you also have to span the vector space. If V1 through Vp doesn't span V, then it's not a basis. So for example, the set V1, which is just 1, 0, is linearly independent, but it is not a basis for R2. Number 53. If the span of the vectors V1 through Vp is equal to V, then some subset of V1 through Vp is a basis for V. This is true, and this is one of the big results of the spanning set theorem. Number 54. If the dimension of V equals P, and the span of V1 through Vp is equal to V, then the set V1 through Vp cannot be linearly dependent. This is true, and the reason is, if V1 through Vp was linearly dependent, then it has some linearly independent subset that spans V. This would imply that the dimension of V is less than P, right? Because if it has a spanning set that contains fewer than P elements, its dimension is going to be at most that size. But we said that the dimension of V is equal to P. Therefore, the set V1 through Vp is linearly independent. Number 55. A plane in R3 is a two-dimensional subspace. This is false. The plane needs to contain the origin. A plane in R3 that doesn't go through the origin is not a subspace, right? What are the conditions of a subspace? Is it first has to contain the zero vector, right? So it's important. A plane through the origin in R3 is a two-dimensional subspace, but not all planes are. Number 56. The non-pivot columns of a matrix are always linearly dependent. This is false. Again, a good way to check this is false is just come up with a basic example and see if it holds for that example. So here, if we have A is the matrix 1, 0, 1, 0, then the second column of A is its only non-pivot column. And since there's one non-pivot column and it's not the 0 column, it's automatically linearly independent. Number 57. Row operations on a matrix A can change the linear dependence relation among the rows of A. This is true. For instance, if we take the matrix 1, 1, 1, 1 and multiply the second row by 2, that's a row operation. So we have the new matrix 1, 2, 1, 2. The relations amongst the rows of the first matrix are row 1 equals row 2. The relations among the rows of the second matrix are row 1 equals 2 row 2. 2 row 1 equals row 2. Those are different relations. Number 58. row operations on a matrix can change the null space. That's false. The reason is if A and B are row equivalent, then AX equals 0 and BX equals 0 have the same solution set. If they didn't, then we would not care about row operations in the first place. So the reason why we use row operations and the reason why they're useful is that they don't change the solution set. And the null space could be seen as the solution set of AX equals 0. Number 59. The rank of a matrix equals the number of non-zero rows. This is false. The rank of a matrix equals the number of non-zero rows if the matrix is in echelon form. And this number happens to be the number of pivot columns too. Number 60. If an m by n matrix A is row equivalent to an echelon matrix U, and if U has k non-zero rows, then the dimension of the solution space of AX equals 0 is m minus k. And this is false because A has n columns, k of them are pivot columns. That comes from the fact that U has k non-zero rows. Each row would correspond to a pivot column. So the dimension of the solution space of AX equals 0 is the number of columns minus the number of pivot columns, so n minus k. 61. If B is obtained from the matrix A by several elementary row operations, then the rank of B is equal to the rank of A. And this is true. The rank of a matrix is the number of pivot columns, and this does not change under row operations. Number 62. The non-zero rows of a matrix A form a basis for row A. This is false. Spoiler for the next question. This is false. This is only true if A is in echelon form. So here, if A is the matrix 1, 2, 1, 2, then the row space of A is spanned by the vector 1, 1. Okay? Even though 1, 1 and 2, 2 are both the rows of A, you don't need them both to write out the row space of A. So the way you'd find a basis for the row space of A is reduce A into echelon form, and then those rows form a basis for row A. Those non-zero rows do. All right, now we'll see 63. If matrices A and B have the same reduced echelon form, then the row space of A is equal to the row space of B. This is true, and the reason is you find a basis for the row spaces of these matrices by putting the matrix into echelon form or reduced row echelon form. And so the reduced row echelon form tells us exactly what the row space is. So if two matrices have the same echelon form, they're going to have the same row space. Number 64. If H is a subspace of R3, then there is a 3 by 3 matrix A such that H is the column space of A. And this is true. And so since H is a subspace of R3, we know its dimension is at most 3, right? Every subspace of R3 either has dimension 0, 1, 2, or 3. You can't have a higher dimension than the entire vector space. Which means we could find 3 vectors in R3 that span H. Maybe it's not a basis for H. Maybe the dimension of H could be smaller, but there's going to be no more than 3 vectors that it takes to span H. And we could make a matrix with these vectors as the columns. And then so clearly, the column space of that matrix would equal H. Number 65. If A is an m by n matrix and the rank of A equals m, then the linear transformation that sends x to ax is 1 to 1. And this is false. And you could check. A here is a 2 by 3 matrix, and the rank of this matrix, which is 1, 0, 0, 1, 1, 1, its rank is 2. But since there is a column that is not a pivot column, the map that sends x to ax is not one-to-one. Number 66. If A is an m by n matrix and the linear transformation that sends x to ax is onto, then the rank of A is equal to m. That's true, because the map that sends x to ax is onto tells us that every row contains a pivot. And so, in the number of pivots tells us the rank of the matrix. So if all m rows have a pivot, the rank of our matrix is m. Number 67. A change of coordinates matrix is always invertible. And that's true. The reason is the columns of a change of coordinates matrix are linearly independent since they are the coordinate vectors of a basis. So the coordinate vectors of a basis are going to be linearly independent. And we know that a square matrix with linearly independent columns is always invertible. In fact, the inverse of a change of coordinates matrix is also a change of coordinates matrix. Number 68. If B equals B1 through Bn and C equals the set C1 through Cn are bases for a vector space V, then the jth column of the change of coordinates matrix that sends B to C is the coordinate vector, the B coordinate of Cj. And that's false. The jth column of the change of coordinates matrix is going to be the C coordinate vector of Bj. I would recommend looking back in the book or your notes to find exactly how do we find the change of coordinates matrix. Chapter 5. Eigenvalues and Eigenvectors. One of my personal favorites. Number 69. If A is invertible and 1 is an eigenvalue of A, then 1 is also an eigenvalue of A inverse. And that's true. Since 1 is an eigenvalue of A, there's a vector such that AV equals V, right? 1 would be AV equals 1 times V. We could multiply this equation by A inverse, and we get that V is equal to A inverse V. So that shows that 1 is an eigenvalue of A inverse. Number 70. If A is row equivalent to the identity matrix, then A is diagonalizable. This is wrong. If we take A to be the matrix 1, 0, 1, 1, this is row equivalent to the identity matrix, but it is not diagonalizable since the dimension of its only eigenspace is 1. So what I recommend you doing is showing that what my conclusion is actually accurate. Find the eigenspace corresponding to 1 and show that its dimension is 1. I didn't do that, but that's good practice for you. Number 71. If A contains a row or columns of zeros, then 0 is an eigenvalue of A. And this is true. If A contains a row or column of zeros, then its determinant is 0. And we know that any matrix with determinant 0 has 0 as an eigenvalue. Number 72. Each eigenvalue of A is also an eigenvalue of A squared. And this is false. So here we have the matrix A, which is 2, 0, 0, 1. So A squared is 4, 0, 0, 1. Since A is an upper triangular matrix, or a diagonal matrix in particular, you could get its eigenvalues by just reading off the entries of the main diagonal. So we see that 2 is an eigenvalue of A, but it's clearly not an eigenvalue of A squared. The eigenvalues of A squared are 4 and 1. Number 73. Each eigenvector of A is also an eigenvector of A squared. So we showed for 72 that the eigenvalues don't pass through squaring, but maybe the eigenvectors do. And this one's true. And let's show it. So let's say that lambda, or that V is an eigenvector for A corresponding to eigenvalue lambda. So that means AV equals lambda V. So let's take A squared V and see what happens. Well, A squared V is equal to A times AV. And we know that AV is equal to lambda V, so this is equal to A lambda V. Lambda is a scalar, so we can move it to the front, so that's lambda AV. But again, AV is lambda V, so we get lambda squared V. So V is an eigenvector for A squared, and its corresponding eigenvalue is lambda squared. Number 74. Each eigenvector of an invertible matrix A is also an eigenvector of A inverse. And this is true. And the reason is, well, since A is invertible, we know that 0 is not an eigenvalue of A. And so we could write out if AV equals lambda V, we want to show that V is an eigenvector for A inverse. Well, we can multiply both sides of this equation on the left by A inverse. So we get V is equal to lambda A inverse V. And then we could divide both sides of the equation by lambda since it's not equal to 0. And this tells us that A inverse V is equal to 1 over lambda V. So V is also an eigenvector for A inverse, and its corresponding eigenvalue is 1 over lambda. Number 75. Eigenvalues must be non-zero scalars. That's false. If AV equals 0, then 0 is an eigenvalue of A. There's no condition that says it can't be 0. Number 76. Eigenvectors must be non-zero vectors. This is true. And the reason why it's true is it's just part of the definition of an eigenvector. If we allowed 0 to be an eigenvector, then it's an eigenvector for every matrix, and it would be telling us nothing new. It would be like the trivial eigenvector. So we just say it's not an eigenvector. Number 77. Two eigenvectors corresponding to the same eigenvalue are always linearly dependent. And that's false. So if we take A to be the identity matrix, then the vectors 1, 0 and 0, 1 are both eigenvectors corresponding to eigenvalue 1, but they are not linearly dependent. Number 78. Similar matrices always have exactly the same eigenvalues. And this is true, and so let's see why it's true. So if A and B are similar, then we could write A as PB P inverse. So we'll take some eigenvector and eigenvalue corresponding to A. So we'll say that AV equals lambda V. Then we could replace A with PB P inverse. So PB P inverse V is equal to lambda V. That didn't show us that we have the same eigenvalue yet, but we can multiply both sides by, we could multiply on the left of to both sides of this equation by P inverse to get B P inverse V is equal to lambda P inverse V. And so this shows that A and B both have lambda as an eigenvalue. The corresponding eigenvector for A would be V. The corresponding eigenvector for B would be P inverse V. Number 79. Similar matrices always have exactly the same eigenvectors. Well, based on our last calculation, it seems like this should be false. And it is false. So if we take A to be the matrix 2, 0, negative 1, 1, we could show that it's similar to the diagonal matrix 2, 0, 0, 1, which is the middle of this expansion here. A has 1, 1 as an eigenvector. But if you take 1, 1 and multiply it to the matrix 2, 0, 0, 1, you get 2, 1. This is not a scalar multiple of 1, 1. So A and B, even though they're similar matrices, do not have the same eigenvectors. Number 80. the sum of two eigenvectors of A is also an eigenvector of A. This is false. So if A is the matrix 2, 0, 0, 1, then 1, 0 and 0, 1 are both eigenvectors of A. So you should check that this is true. Okay, so you should check that. If this was a homework assignment or on a test, you would want to prove that what I said is true. But if we were to take the sum of these two vectors, which is 1, 1, multiply it to A, we would get 2, 1, which is not a scalar multiple of 1, 1. So it is not an eigenvector of A. Number 81. The eigenvalues of an upper triangular matrix A are exactly the non-zero entries on the diagonal of A. This is false. You could have 0 on your main diagonal, and that could be an eigenvalue. So the eigenvalues are every entry on the diagonal, not just the non-zero ones. Number 82. The matrices A and A transpose have the same eigenvalues, counting multiplicities. This is true. And the reason is, well, the transpose of A minus lambda I is equal to A transpose minus lambda I. So the determinant of A minus lambda I is equal to the determinant of A transpose minus lambda I. So A and A transpose have the same characteristic equations, which means they have the same eigenvalues, counting their multiplicity. Number 83. If a 5 by 5 matrix A has fewer than 5 distinct eigenvalues, then A is not diagonalizable. Well, this is false. You could take A to be the identity matrix. And the identity matrix is a diagonal matrix, so it's clearly diagonalizable. And it has only one eigenvalue, and that's 1. Number 84. There exists a 2 by 2 matrix that has no eigenvectors in R2. And this is true. The eigenvalues of the matrix 0, negative 1, 1, 0 are plus or minus I, the complex number I. And their vectors, their eigenvectors, are scalar multiples of I1 and negative I1. Note that I wrote Eigenvectors, but I'm not changing that. Number 85. If A is diagonalizable, then the columns of A are linearly independent. This is false. The matrix 1, 0, 0, 0 is a diagonal matrix, so it's diagonalizable, but one of its columns is 0, is the 0 vector. So the columns are clearly linearly dependent. Number 86. A non-zero vector cannot correspond to two different eigenvalues of A. That's true. And so the way we would show this is we would do some sort of, proof by contradiction type thing. We would say if AV equals lambda 1V and AV also equals lambda 2V, then lambda 1V equals lambda 2V. And this can't happen if V has a single non-zero entry. And we said that V is not the zero vector, so this would conclude that lambda 1 equals lambda 2. So you can't have different eigenvalues for the same eigenvector. Number 87. A square matrix A is invertible if and only if there is a coordinate system in which the transformation x to ax is represented by a diagonal matrix. And this is false. If we take A to be the matrix 1, 0, 0, 1, well, A is a diagonal matrix, so the transformation that sends x to ax is represented by a diagonal matrix, but A is not invertible. Number 88. If A is similar to a diagonal matrix B, then A is also diagonalizable. Sorry, if A is similar to a diagonalizable matrix B, then A is also diagonalizable. This is true. So let's say A is similar to B. So A equals P, B, P inverse. And B is similar to a diagonal matrix, which we'll call D. So B equals Q, D, Q inverse. Well, then we can replace B with Q, D, Q inverse, and we get A is equal to P, Q, D, Q inverse, P inverse. So A is equal to the matrix PQ times the diagonal matrix D times PQ inverse. So A is also diagonalizable since it's similar to a diagonal matrix. Number 89. If A and B are invertible n by n matrices, then AB is similar to BA. This is true, and again, maybe it's not immediately obvious why it's true, but let's see how to work it out. So AB, we could multiply on the right by A inverse. Okay, so AB equals A inverse. But instead of having the first AB grouped together, we could group together the B and A in the center. So AB is equal to A times BA, A inverse. So AB is similar to BA. Number 90. An n by n matrix with n linearly independent eigenvectors is invertible. That's false. So the matrix, again, we've used this 2 by 2 matrix so many times. It's a good one for counterexamples. So if A is the matrix 1, 0, 0, 0, then 1, 0, and 0, 1 are both eigenvectors and they're linearly independent. But our matrix is not invertible. So this is saying the linear independence of our eigenvectors tells us nothing about if our matrix is invertible or not. Our final chapter, chapter 6, orthogonality and least squares. Number 91. The length of every vector is a positive number. Well, that's false, because the length of a zero vector is 0. The length of any other vector sure is positive, but the length of the zero vector is 0, which is not positive. Number 92. A vector v and its negative v, have equal lengths. This is true. So remember, the length of the vector is the square root of v dotted with itself. The length of negative v is the square root of negative v dotted with negative v. We could pull out the negative ones, so that's the square root of negative 1 squared times v dot v. Well, negative 1 squared is 1, so this is just the square root of v dot v, which is the length of v. Number 93. The distance between u and v is the length of u minus v. That's true. That's literally the definition of the distance between u and v. Nothing to show here. Number 94. If r is any scalar, then the length of rv is equal to r times the length of v. And this is false. The length of rv is equal to the absolute value of r times the length of v. If v, for instance, if v is the vector 1, 0 and r is negative 1, well, then the length of rv is 1, and that's not equal to negative 1. Number 95. If two vectors are orthogonal, they are linearly independent. And I know what you're thinking. Oh, we proved this in class. It's obviously true. Well, it's false. If one of the vectors is the 0 vector, well, 0 is orthogonal to everything. And you can't have linear dependence when you have the 0 vector. Now the question is, if this said if two vectors are two non-zero vectors are orthogonal, well, that would be a totally different question, and you should check. Is it the case that they're linearly independent if they're non-zero? Number 96. If x is orthogonal to both u and v, then x must be orthogonal to u minus v. Well, let's see. That's true. So x is orthogonal to both u and v. That means x dot u is 0, and x dot v is also 0. So x dot u minus v, we could distribute the dot product. So that's x dot u minus x dot v. 0 minus 0 is 0. So x is orthogonal to u minus v. Number 97. If the length of u plus v squared equals the length of u squared plus the length of v squared, then u and v are orthogonal. This is true, and maybe it's not immediately obvious why. So let's take the length of u plus v squared. We could write that as u plus v dotted with itself. Distribute this out, and you get u dot u plus 2 u dot v plus v dot v. And this is equal to the length of u squared plus 2 u dot v plus the length of v squared. And we're saying that's equal to the length of u squared plus the length of v squared. You could subtract off the length of u squared plus the length of v squared from both sides, and you're left with 2 u dot v is equal to 0, which means that u dot v equals 0 and u and v are orthogonal. Number 98. If the length of u minus v squared is equal to the length of u squared plus the length of v squared, then u and v are orthogonal. Again, it's the same exact math as the last one, except wherever we had a plus, it's switching to a minus. And it's going to, if we work it out, I'm not going to talk through it. You could pause and look through it yourself, but it's going to imply that minus 2 u dot v is equal to 0. So again, u dot v equals 0 and u and v are orthogonal. Number 99. The orthogonal projection of y onto u is a scalar multiple of y. This is false. The orthogonal projection of y onto u is a scalar multiple of u. And this should be immediately obvious when you look at the formula for the orthogonal projection of y onto u. It's a scalar times u. Number 100, the big 100. If a vector y coincides with its orthogonal projection onto a subspace W, then y is in W. And this is true. And the reason is the orthogonal projection of y onto W is an element of W. So if y is equal to an element of W, it's obviously an element of W. Number 101. The set of all vectors in Rn orthogonal to one fixed vector is a subspace of Rn. This is true. So if we take W to be the span of this one fixed vector, well then that's a subspace of Rn. And then the set W perp, which is the set of all vectors orthogonal to V, is also a subspace of Rn. Right? The perpendicular complement, the orthogonal complement of a subspace is a subspace. We proved that in class, and feel free to prove it again for practice. Number 102. If W is a subspace of Rn, then W and W perp have no vectors in common. This is false. The 0 vector is in both W and W perp. And again, feel free to show that, prove that 0 is in both of these subspaces. Well, they're subspaces, right? So 0 has to be in them. There's not much to prove. Number 103. If the set V1, V2 is an orthogonal set, and if C1 and C2 are scalars, then C1, V1, C2, V2 is an orthogonal set. Well, this is true. And so let's just check to see if C1, V1 dot C2, V2 is 0. Well, C1, V1 dot C2, V2, we could factor out the scalars. And we have C1, C2 times V1 dot V2, which we know is 0. So C1, C2 times 0 is 0. We have an orthogonal set. A good thing to ask is, what if we had more vectors? V1 through Vn was an orthogonal set, and C1 through Cn were scalars. Would we still have an orthogonal set? Number 104. If a matrix U has orthonormal columns, then U transpose equals the identity matrix. Well, let's check. This is false. And the reason is, let's take a matrix with orthonormal columns. Right? What's it mean to be orthonormal? That means they're pairwise orthogonal. So if you take the dot product of any two columns, you get 0, but the length of each column is 1. So it has orthonormal columns. And if we do the matrix multiplication, U times U transpose, we get a matrix that's close to the identity matrix, but it's not quite the identity matrix. Number 105. A square matrix with orthogonal columns is an orthogonal matrix. So this is testing if we know what the definition of an orthogonal matrix is. And it's false. We need a square matrix to have orthonormal columns to be an orthogonal matrix. So this is just testing if we know definitions. Number 106. If a square matrix has orthonormal columns, then it also has orthonormal rows. This is true. So we know if U is a square matrix with orthonormal columns, then U transpose U is the identity matrix. And since U is square, this tells us that U inverse is U transpose. The inverse of U is U transpose. So we could actually multiply U on the right by U transpose to still get the identity matrix. But U is U transpose transpose. So this tells us that the columns of U transpose are orthonormal. And the columns of U transpose are the rows of U. Number 107. If W is a subspace, then the projection onto W of V squared plus the length of the projection onto W of V squared plus the length of V minus the projection onto W of V squared is equal to the length of V squared. And this is true. This is the Pythagorean theorem. In this case, the length of V would be the hypotenuse, and the lengths of the other sides squared would be on the left-hand side. Right? And that's because the projection onto W of V is orthogonal. It's an orthogonal projection. We have a right angle, so we're allowed to use the Pythagorean theorem. Number 108. We're almost there. A least squares solution of AX equals B is the vector AX hat in the column space of A closest to B that satisfies the distance between B and AX hat is less than or equal to the distance between B and AX for all X. This is false. The least squares solution is the vector X that satisfies that. It's not the vector AX. Okay, so we're looking for the X, our input, our vector X hat. Number 109, the final question. The normal equations for a least squares solution of AX equals B are given by X hat equals A transpose A inverse A transpose B. And this is false. And the reason is A transpose A is not necessarily invertible. So if A transpose A doesn't have an inverse, this formula doesn't make any sense. And we know that A transpose A is invertible if and only if the columns of A are linearly independent. Well, we did it. 109 linear algebra true or false questions. Let me know in the comments how many you got right. Did you get all 109? If you did, I'm sure you're going to ace your final. Make sure to subscribe if you want to see more videos like this. It'll really help the channel. Well, I'll see you next time. Don't text and drive. Bye-bye.